the mechanical engineering department, and he does his research at the LaMCoS laboratory, mainly on multiscale numerical models for engineering applications under severe loading. And he's going to speak today of virtual charts or twins for real-time simulation in computational mechanics. Welcome, Anthony.
Okay, thank you. Thank you very much, Valérie, for this introduction. So I'm very happy to be here this morning for this Slide Science event number 6 on machine learning. So the aim of my talk today concern the development of virtual charts or virtual twins, as I will explain later, for real-time simulation in computational mechanics. Okay, so in order to develop a general framework for virtual twins, I propose in this first part to focus on process simulation. For instance, in a general point of view, we can consider a model which allows to describe the physical content of a process. And here we can consider the following set of equations based on different quantities. You have a possible dependency on X here, which concerns the space, the 3D space, the time dependency, the T parameter, and also other parameters, which can be geometric parameters, material parameters, or parameters linked to the load, or boundary conditions, for instance, for engineering application. And the general strategy concerned not only the development of such models, but also the ability of the model to give information of possible quantities of interest in order to improve, for instance, a process. Okay, so in practice, the problem deals with high-dimensional space, as you can see here, 3 for the space, 1 for the time, and n for possible other parameters. In this course this morning, we will consider until 10 multi-parameter space of dimension 10, sorry. However, we can increase quite easily the proposed strategy to other high-dimensional space. What is interesting here is to understand that we have a difficulty linked to the high dimensionality of such problems. Furthermore, such problems can be highly nonlinear, non-smooth, with possible dissipation. And also it concerns transient nonlinear simulation with possible coupling between different physics and different scales. Generally speaking, you have also a picture here. In fact, this picture is interesting because it concerns an hypercube of dimension 11. And as you can see here, in such multi-parameter space, the difficulty concerns the ability to compare different points inside this hypercube or different snapshots if we focus on a snapshot. Generally speaking, we can talk about data, and here the main difficulty is the possibility to compare different data in this multi-parameter space. In this course, I will focus on physical modeling of different nonlinear dissipative phenomena, which can concern the simulation of different kinds of processes, for instance, welding. And as you can see here, we can, in a course description here, introducing a general strategy in order to model a problem. And generally speaking, the standard strategy concerned at first different observed physics and from balance equations, which are well known in physics, we can model a given nonlinear problem, and the recent developments on computational mechanics, on computational physics in general, deals with the ability to solve such a set of partial derivative equations in practice. And more recently, as you know very well, the science of data is a new paradigm, in fact, to describe what happens in the observed physics. And the new paradigm allows, in fact, another strategy in order to couple the data directly from experiments to a given model, for instance, as you can see here, from, for instance, the proposed strategy of Ortiz. Here, the dots, the red dots, concern possible data from experiments, and the blue curve concerns a subspace here. If we focus on a 2D modeling of the global strategy, and the blue curve concerns balance equations, and we can imagine to develop iterative strategy between the data and balance equations, and at convergence, it is a good compromise between data from experiments and possibility to ensure balance equations from a given physics. So the motivations today are to be of different kinds. The first one is the ability to develop accurate and efficient models with the ability to use these models in real time, as we will see later. And in this case, there is a strong link, in fact, in the development of virtual charts or virtual twins. And we will see later that the general idea, in fact, concerns a first step, an offline step, which consists in building, in fact, a twin, a virtual twin, which has the ability to give an answer in real time. Real time is a specific concept that I have also to define later, because real time depends on the time scale that you want to consider. And so this virtual twin can either be based on reduced order models, as we will see, for instance, the simulation of a welding process, or it can be based on data-driven computational mechanics or data-assisted multiscale computational mechanics, depending on the way you follow the different scales, from the bottom-up predictive models or top-down design modeling. And I will give you some examples of this kind at the end of this course. If I come back to process simulations, the standard approach, as you can see here, consists in defining a four-dimensional transient nonlinear model of such a process. It concerns a coupling model between thermal and mechanical effects. And the idea is to be able to develop a virtual chart instead of developing a costly numerical model based on the approximated solution of a complex set of partial derivative equations by a new virtual chart, which is a summary of such a model, which is built offline and then which can be used in an online stage in order to study, for instance, different kinds of quantities of interest. Here in mechanical engineering, we focus on, in practice, on fields such as the temperature field, the stress field, or, for instance, for a process such as welding, we are interested in distortion fields, for instance. So the idea is to be able to build real-time simulation for the real-time simulation with possible dependency on different kinds of parameters. These parameters can be material parameters, the yield stress, parameters from thermal effects, or parameters from the load. Here, for instance, the velocity of the heat source can be a parameter of such a virtual chart. Furthermore, here we propose to develop virtual charts which are non-intrusive. It means that, for instance, if you use a finite element software, we want to be able to use it in the offline stage with no development inside this software. It can be a commercial software, for instance, and we want to use it with no specific developments in order to build the virtual twin. So reduced order models offer a very interesting way in order to reach this goal, in order here, for instance, to obtain an efficient virtual chart, virtual twin of the process, in order to be able to use it in real time. Furthermore, what is interesting in such approaches, you have either two kinds of reduced order models. In fact, we have in the literature mainly a priori reduced order models, which can be used on the fly during a nonlinear simulation, and you want to increase the efficiency of the solver, for instance, in order to have an efficient solver, in order to obtain a good solution in a reduced CPU time. And on the contrary, we have also a posteriori reduced order models, which are based on two steps, an offline step and an online step. The idea here is to be able to introduce, in fact, a memory effect in simulations, in computational mechanics. This memory effect here is what I call the offline stage, where you use, for instance, finite element software in order to build at a given level of accuracy such a virtual twin. Furthermore, this virtual twin has to be frugal. In other words, this memory size has to be optimized. Okay. Generally speaking, we will see also that after having built such a virtual chart or virtual twin, we have a set of snapshots. A snapshot, for instance, is a four-dimensional calculation which allows to describe the physical content of the welding process, for instance. So imagine that you have a multiparametric space with different snapshots. The general difficulty, in fact, after having developed in the offline stage the virtual chart, is to be able to use it in real time on the online stage. And in this case, when you ask the virtual twin to give you an answer on a specific quantity of interest, you have to proceed to an interpolation, an efficient interpolation, because the quantity of interest is not calculated in the previous offline stage. So you have to proceed to interpolation. And what I want to say here is that, in general, a multiparametric space in physics based on balance equations is not a Euclidean space. Okay? It is not a Euclidean space. It means that between different snapshots, the standard linear interpolation is not the good way to proceed to interpolation between snapshots. In fact, based on the fact that such a multi-parameter space with high dimension, for instance 10 or 11, is not Euclidean, it concerns, in fact, in a general point of view, what we call nonlinear manifolds. Okay, so in such a case, when we develop virtual charts or virtual twins from physics based on nonlinear governing equations, the multiparametric space is a non-Euclidean manifold. In other words, a subspace of such a multiparametric space is not a straight line between two snapshots. So the difficulty here is to be able to interpolate in such a nonlinear space, a non-Euclidean space, and a very efficient way is to be able to build a tangent space at a given snapshot. And this tangent space, according to differential geometry, is we know that there exists an Euclidean one, an Euclidean manifold locally close to a snapshot. Okay, this is the idea. So instead of interpolating linearly between two snapshots, we propose what we call Grasmann manifolds interpolations, which are very, very efficient for reduced order model based on separated variable representation of the multiparametric space. In other words, here we at first proceed to a logarithmic mapping between a snapshot. Here it concerns the snapshot M1. And after the logarithmic mapping on the tangent space tangent to the snapshot M0, after that we can proceed to a linear interpolation on the tangent space. Okay? The set of tangent space in differential geometry in fact allows to proceed to linear interpolation, and then after that you can come back to the non-Euclidean manifold by the inverse mapping of the logarithmic mapping. Okay, this is the idea. So here, a very simple subspace is modeled by a circle, and the new snapshot, M new, concerns the interpolation between M0 and M1, and it is very efficient. Okay, more accurate, as you can see here, for instance, when we focus on the error, global error, standard error, on the snapshot M new and compared with the exact solution. Okay, so when you use reduced order models in multiparametric space, Grasmann manifold interpolation are very efficient way when you have a separated variable representation of the multiparametric space. For instance, in the 2D case, if you have a multiparametric space of dimension 2, you can use the singular value decomposition in order to obtain a separated variable representation of this two-dimensional space, and then you can use such interpolation techniques. The idea here is that the multiparametric space is non-Euclidean. It is fundamental to understand such methods. Okay, so here, for instance, you have an example of such separated variable representation of the welding process. Here it is a four-dimensional simulation of the welding process, 3D in space, 1D in time, with possible other parameters. Okay, so it is a complex calculation, 2 or 3 hours with a finite element software, because it is a transient thermal simulation with a nonlinear dissipative model for the mechanic part, elastic, plastic, plus different nonlinear effects in the material. So the coupling of such, the multiphysics coupling of such a model involves transient space-time simulations. And here we have plotted the 3 first space modes, gamma 1, sorry, multiplied by gamma 1, gamma 2, and gamma 3. And here, the aim of this slide is to show you that what is important in such nonlinear examples is the time dependency. The time dependency here is, you can find the time dependency of the problem in the transient thermal effects, and also in the fact that you have elastic plastic model, for instance. So there is a history effect. You have internal variables or hidden variables that allows to describe plasticity, elastic plastic models. Okay, so such models, even in quasi-static, have a strong time dependency. And when you want to build efficient reduced order model in this case, or virtual twins, you have to account for the time dependency of this problem. So here we can proceed, for instance, to a singular value decomposition, and then we can plot the solution as an approximation of the sum from 1 to n to a product of space function multiply time functions. Okay? And gamma 1 multiplies the first space mode, gamma 2 multiplies the second space mode. And here you have the time modes. What is interesting in the 2D case is that, based on the SVD, is that we have a very nice orthogonal property between the space mode and the time modes. Furthermore, we can calculate the energy content of each mode. So for instance, the first space-time mode, gamma 1, the time mode multiplies the space mode, has a high level of energy. I mean in terms of contribution in the global solution. And then the energy decreases according to mode 1, mode 2, and so on. Okay, so the general strategy is the following. Instead of developing learning methods and so on, I prefer to use the concept of virtual twin or digital twin, as I explained in this slide. In fact, this afternoon with Paco Ginesta, you will discuss more accurately on the concept of digital twin or virtual twin, or more generally, the concept of hybrid twins. So here, what I call a digital twin or virtual twin is simply an executable model, virtual model, with a strong physical content. Okay, the different constraints that I add to such a virtual twin is that it has to be physically based, it has to be accurate and efficient, and also it has to be frugal, as I have explained before. Fundamentally, it is a physically based model. So either you have balance equations, the first principle of thermodynamics, the second one, and linear and angular momentum, and balance of mass, for instance, okay? Or you can keep a set of such equations, and you can, for instance, only concern data from experiments which concern the material stress-strain law, for instance, of the system. Okay, but globally, we want to keep the spirit of balance equations in physics, the Newton law, and first and second principle of thermodynamics. Okay, in such an approach. I propose to give you a first example. So as I have explained before, the development of virtual twins for real-time parametric studies and application to welding process. It is based on a specific reduced order model, which is an a posteriori one, the high order proper generalized decomposition, which is a specific, which is a variant, in fact, of the proper generalized decomposition proposed by Paco Ginesta more than 15 years now. And we will see that it is a good way to build efficient virtual twins. We will see in this case what I mean by efficient. So the welding process is of interest, for instance, in engineering applications, as you can see here, either in the aeronautical applications or for nuclear power plants applications, many applications. So it is even today a process of great importance in such applications. And what we have to develop in this case, what we want to propose is a virtual twin of such a process for many reasons. For instance, imagine that you have a virtual twin which concerns the simulation of such a process, which is a multiphysics and multiparametric problem, because it depends not only on the space and time. It is not only nonlinear and transient model, but also it depends on many other parameters, such as material parameters, thermal parameters, or mechanical parameters. And also it depends on, for instance, the heat source, the intensity of the heat source, the velocity of the heat source, here, based on a laser, as you can see on this slide. Furthermore, you can have other parameters, for instance, geometric parameter, the thickness here of the two plates that you want to use in this process, because you can have a strong dependency on the different quantities of interest. I mean, the stress field, the temperature field, or the distortion field, on all these parameters, material parameters, boundary conditions, loads, or geometric parameters. So the main problem that we have in such nonlinear simulations is that it is very expensive in a numerical point of view, even today. So what we want to have is a real-time simulation for such problems. So what is the interest of developing such virtual twins, for instance, for optimization? We want to optimize the process, or for identification. Imagine that you have on specific material parameters a high level of error, or it is not so easy to proceed to identification in such models. So we can use also a virtual twin with a parameter linked to material parameters in order to proceed to identification compared to data from experiments. We can also account for uncertainties and the dependency of the uncertainties on specific parameters. Okay. So the idea is to avoid the use of three finite element software and consider, on the contrary, virtual twins, which allow the real-time use of such model. So here I propose to give you an example of such a model. Okay, so here, before showing you how it works and how it is developed in a theoretical point of view, I propose to show immediately a virtual twin on welding process. Okay, so here it is in real time. You have a user which fixes different parameters. There are 6 parameters. In fact, in this case, the multiparametric space is of dimension 10 because you have 3 dimensions for space, 1 for time, and you have also 6 other parameters. Cp is the thermal capacity, and you have also thermal parameters alpha. You have the yield stress, the Young modulus, stress hardening, and Q is the intensity of the heat source. Okay, so you can fix all the parameters. Okay, and in real time, this is an example of virtual chart that we are able to build today. You have the transient space-time simulation of the process. Okay, so this is of great interest in order to improve the process or for identification and many applications, as we will see later. Okay, so in fact, this is a quite surprising for the first time when you discover such virtual twin, but it is possible to do that today, to develop such a virtual twins based on an offline stage, which consists in learning, in fact, such nonlinear simulations. You can store this virtual twin. You can increase the information that you put in this virtual twin in order to be more accurate and so on, to increase the possible values of the parameter. Okay, so what is interesting here is that you store information, in fact. You don't need to proceed to new very close calculations that you have done before. So it is a new paradigm, in fact, in numerical simulations, in computational mechanics. Okay, so how it works? What we want, first of all, for the construction of virtual twins is high fidelity welding simulation, okay, of the process with a non-intrusive approach. If you use a given specific dedicated software for welding simulation, we want to optimize the storage of this virtual twin, okay, and also we want to be frugal, okay. I think that it is, when you develop numerical models, in fact, you want to have a good level of accuracy, you want to be efficient, okay, you want to be stable and so on, and robust, but also I think today that we have to be frugal in terms of numerical simulations. Okay, expensive simulations are not frugal, so I think that it is today a good way to choose between different kinds of numerical methods. Okay, and we want to guarantee a good level of accuracy for this virtual twin. And at the end here, we want the ability of the virtual twin to give an answer on real time. Okay. For instance, real time, depends on the use of the virtual twin. For instance, if you are an engineer and you want to use this virtual twin in order to have to help you for making a choice between different parameters, so 1 or 2 seconds is enough. I mean, in this case, to help an engineer to choose between different parameters. But if you want, for instance, to develop a feedback between the process in real time and the virtual twin, then in this case, real time means 0.001 seconds. Okay, if you want to couple the process, the true process, and the virtual twin, for instance, it can be of great interest in practice. Then the real-time answer has not the same time scale. So the real-time here depends on the use of such a virtual twin you want to do. Okay, generally speaking, the theoretical concepts are simply singular value decomposition or extensions to this concept. The singular value decomposition is no more, in fact, in my point of view, if you have multiparametric space, a sum of product of 1D functions. But the singular value decomposition is only available in 2D spaces, so the extension to n-dimensional spaces, for instance, can be there are many ways to extend this to n-dimensional spaces. For instance, the proper generalized decomposition. So here you have at the end a field which is U, which depends on space, on time, on mu1 until mu_n for n other parameters, no more than a sum, an approximation based on a sum of a product of 1D functions. Okay. And such an approach, such a representation is very interesting for virtual twins because in the multiparametric space, it is of great interest for real-time simulation. If you want to have the answer in a very short time, it is very easy to give you the answer when the approximation is based on a product of a sum of a product of 1D functions. The idea here is that, in fact, you have a tensor separate tensor product representation of the solution. Okay, so many ways to develop this according to the fact that you have a weak form, a variational form, or a strong form. I will not give you some detail at this level of the discussion. But at the end, what we want to have is an efficient way to build such virtual twins, and in order to have its ability to have an answer in real time. Okay, so based on this, we are able to build a reduced order model. For instance, you can use a part of this decomposition. You can store the different modes. Mode 1 is the product of each 1D function for each parameter. Mod 2 is the product of all the other 1D functions for each parameter, but at corresponding to mod 2 and so on. So mod 1, mod 2, and so on allow to build what we call a reduced order model. In other words, we can, instead of solving, for instance, a linear problem which can come from finite elements, K is a stiffness matrix, U is a set of doves for the displacement field, and on the right-hand side, you have the external load, for instance, and in this case, you can reduce such a problem on a subspace based on the first modes instead of solving the full problem of dimension the number of doves, which can be very big. Okay, so the idea is very simple in this case. You can use this 1D separated variable representation in order to build a reduced model, and we will see after that how to generalize such an approach to n-dimensional multiparametric spaces, nonlinear transient problems, which can depend on space and time and also all the parameters. And here, don't forget the ideas that I have introduced before, also the ability, for instance, to interpolate between two snapshots in a non-Euclidean manifold. It is based on the Grasmann manifold introduced in such applications by Amsalem more than 10 years ago, and Professor Farhat. Okay, many other methods to build a reduced order model. But here, the interest of this slide is to focus on the time dependency. Don't forget that such problems highly depend on the time due to the transient thermal effects and also the dissipative effect with possible internal variables in the mechanical model. So what I propose here is whatever is a problem is to introduce the time as a parameter of this multiparametric space. Not only the geometrical space, I mean the 3D material space, but we have also to introduce the time as a parameter in such virtual twins. It is a key point, in fact, in order to be efficient and frugal and to be accurate. The other parameters, as I have explained before, can be material parameters, boundary conditions, external load, or geometric parameters. So the general strategy can be summarized as follows. In order to develop a virtual twin, non-intrusive offline, it is based at first on a non-intrusive offline strategy. In the offline stage, as you can see here, we use, for instance, finite element software in order to simulate the welding process. And then we use this commercial software, for instance, as a black box in order to build snapshots. In fact, we consider that the finite element software is no more than a black box in order to build data. Okay, it is a black box to build data. And the question is where we have to calculate the data in order to be efficient. I mean, the size of the virtual twin depends strongly on the number of data, depends on the snapshot. So we have to develop a specific strategy in order to minimize the number of snapshots in the multiparametric space. Okay, so there are specific strategies for that. And furthermore, we have to reach a given level of accuracy in this virtual twin. It means that when in real time we use this virtual twin, we have to ensure a given level of accuracy for the real-time simulation. So this can be prescribed at the beginning step in the offline stage in order to be sure that whatever is the online use of such a virtual twin, you have to ensure a given level of accuracy. And after this offline stage, which is the learning stage, then we can use this virtual twin or virtual chart, okay, in order to proceed to different use such as optimization, identification, or other kinds of applications. What is interesting here is to define accurately the control parameters. Okay, because in fact, it is dedicated to a given process. Depending on the process, you have to you have to choose accurately the good parameters in order to have an efficient virtual twin. You can add all the parameters of the model, but it is not a good idea because you have to optimize the size of the virtual twin. Okay, so here I propose to focus on the high-order proper generalized decomposition, which is an a posteriori PGD, sorry. Okay, it is not an a priori PGD, it is an a posteriori PGD. It allows to build a posteriori from snapshots, from finite element, space-time finite element simulations of the process, to build a separated variable representation of the multiparametric space, for instance, of dimension 10, as we have seen before, 3D for space, 1D for time, and 6 for other parameters. Here, it consists in this introduction in a very simple model, okay, a simple geometry, with a constant velocity for the heat source. All is given, material parameters for the transient thermal simulation, and also mechanical model, and the geometry, and the finite element mesh, okay? An interesting comment on the weak forms, on this multiphysics formulation of such a problem is that we can have different frames in order to build this virtual twin. The discussion here concerns the choice of the frame that you want to use in order to simulate or to store the information of, for instance, the temperature field or a stress field or internal variable fields. For instance, we have an interesting frame in such an application, which is a moving frame. Imagine that you have a frame linked to the heat source, okay? In this case, I propose to compare the size of the virtual twin, and the dependency of the size of the virtual twin, with the choice of the corresponding frame. Either you consider a fixed frame or a moving frame, and we will see that it has a strong effect on the size of the virtual twin. Okay, so I propose here in this first study to consider a moving frame for the heat conduction problem, for the thermal model, and for the mechanical one, I propose to use a fixed basis, which is a standard approach for such problems. And I propose, as a starting point, to proceed to a singular value decomposition on the space-time solution. Big U depends on space and time here, and vertically we write a given solution at a given time, where small n corresponds to the number of doves, and m the number of time steps. Okay, so it is a rectangular operator. We can proceed to singular value decomposition. In other words, we proceed to a separated variable representation of the space-time problem. The SVD is no more than a sum of a product of 1D function, both in space and time. Okay? And here, the singular values, sigma 1, sigma 2, and so on, correspond, in fact, to the energy contribution of a given mode. And we can also have a good estimate of the number of node givens, for instance, to reach 99% of the solution. It is, I think, interesting to see the shape of such modes. So we have already plotted them. Here you have the space modes, multiply the square root of the singular value mode 1, mode 2, and mode 3, and also you have the 6 first time modes. So the space-time mode is a multiplication of a space mode multiply a time mode, and the first one corresponds to a high level of energy of the solution. So, in fact, an interesting comment here is that when you proceed to a singular value decomposition in space and time of a nonlinear transient problem in physics in general, you can see the physical content of the problem. More accurately, you can see the multiscale content of the solution. Okay, multiscale content of the solution. And here, for instance, I compare the solution, the reduced basis here for the temperature field, either in the fixed frame, this is this slide, and the next slide here consists in plotting the energy content of these modes. And we can see on the left from 0 to 1 the normalized energy of each mode. And in the red, it is the global energy from 1 to close to 100, the last mode, and the total energy from 1 to 100 of the reduced basis. And you reach more than 99% of the energy of the solution with close to 50 modes. So here it is a way to have an estimate of what I call the compressibility of the reduced basis. Okay? So it is a very interesting indicator, because if you proceed to the same analysis in the moving frame, okay? So we have proceeded to the same space-time simulation in the moving frame, and we can see that instead of 35% for the compressibility, we can reach 2.5%. So with a very high level of compressibility for this reduced basis, only by considering the moving frame, because here, as you can see, the 3 first space modes and time modes in the moving frame allow to capture more than 99% of the solution. So here it is interesting also to define efficiently the frames of such transient physical models. Okay, as you can see here on the moving frame, you can see that the first mode is no more than the temperature field close to the source. And the solution is no more than a local thermal field linked to the moving frame of the source. In fact, in this solution, we have not a memory effect. Okay, there is no really memory effect in this solution. This is why the moving frame is very interesting. And if you use stationary calculation here, only 1 mode is enough. So it is the best level of compressibility that we can have if you have a stationary model in the moving frame, I mean for the thermal field. This is in contrast with the mechanical field, for instance, displacement, stress field, plastic strain, or here an internal variable of the model of the elastoplastic model. What is interesting to notice is that whatever is a frame, fixed or moving frame, the level of compressibility is close to 15%, whatever is the field. Okay. Here, it is not possible to reduce the compressibility because you have memory effects, in fact. In the mechanical field, you have internal variables, and such variables are not very easy to reduce, okay, in terms of storage. So there is no really a dependency here on the frame, on the compressibility of the mechanical fields.
Tony, could you precise if in this example the spatial extent of the domain is finite or not? Because it could change the result of your analysis.
Okay, thank you for the question. So here in this case, the spatial discretization is finite. We account for boundary conditions in the 3D. It is a 3D model with finite dimensions on the 3 directions with specific boundary conditions. Yes.
So there is a transient, but it's included in your model analysis.
Exactly. Okay. It is a finite 3D dimension problem with transient thermal effects and nonlinear mechanical effects linked to elastic plastic model with stress hardening and so on, and internal variables. Yes.
Okay, thank you.
Okay. So So it is interesting because when you develop virtual twins, when you develop, in fact, such reduced order models, you have to account for, in my point of view, the level of compressibility that you want to reach. And there are many ways to improve the compressibility of such a virtual twin. Here, for example, the choice of the frame is a key point. And what is interesting also is to make the link between the choice of the frame and the history effects in the different fields. Okay, then to conclude, if you remember the general idea, you have a multiparametric field, big U here, which from 1 to D, the number of parameters, space, time, and other kind of parameters. And the idea is to build a sum of product of 1D functions. In other words, in a separated variable representation of this multiparametric problem. Here, I focus in this introduction on D close to 10, okay? Not 100, 1000, but only 10. It is quite enough for such problems. And in fact, the idea here is to use a canonical decomposition of tensors. Assuming that you have a cuboid here, for instance, then here it corresponds to a sum of the product of 1D functions. It is a canonical decomposition of tensors of order 3. Here we have high dimension tensors in this case, according to D. But whatever is the value of D, we assume that we have an efficient canonical decomposition of such tensors. The problem that we have for D bigger than 2 is that we have no more the Cartung theorem. In other words, there is not unicity in such a decomposition. In other words, the 1D modes are not orthogonal together. Okay, you can build a posteriori an orthogonal decomposition when D is bigger than 2, but this orthogonal decomposition of 1D tensor is not unique. Okay, so there are many ways to do that. There is a toolbox Parafact, for instance, which is available in MATLAB. Okay, but in practice, it is not so easy to use Parafact with D bigger than 5. This is why there are more efficient methods, for instance, in this case. So here we propose to use, instead of such approaches, the high order proper generalized decomposition, which is very efficient in order to build a posteriori 1D decomposition, the sum of 1D functions, separated variable representation of such multiparametric space until 10. Okay, I don't want to focus on the details. I prefer to show you some examples. So it is mainly based on the PGD, but it is an a posteriori PGD. So it is an iterative process based on an alternating fixed point strategy. And we want to minimize the distance between different snapshots. So imagine that you have a set of snapshots and you want to build this 1D decomposition, separated variable representation of the multiparametric field, okay? And at the end, you have a sum of the product of 1D functions. Okay, however, I want to focus on this slide on a technical aspect. It is well known that such approaches, such as PGD, in fact converge slowly because you have not good orthogonal properties between the modes. So you can introduce orthogonal properties in the modes in order to accelerate the convergence, or you can also use very interesting dynamic relaxation techniques proposed, for instance, by Aitken, and it is of great interest in order to improve the convergence rate of such methods in order to recover in a very short CPU time the separated variable representation of multiparametric fields. Okay, so you can here notice this interesting technical aspect in order to have a high order proper generalized decomposition, which is efficient. So some examples here. the standard high-order proper generalized decomposition in order to reach a given level of accuracy in this problem. We have more than 1,000 iterations, and with acceleration techniques, we can decrease such level of iterations by 2 or 3. Whatever is the mode, okay? And I want to conclude also to the building of snapshots. Okay, we have a multiparametric space of dimension 10. Why not? 3 for space, 1 for time, and also 6, for instance, for other parameters. But the question is, if you calculate, if you remember at the beginning, imagine that you have a multiparametric space of dimension, okay, of dimension 11. Okay, this is an hypercube of dimension 11. How many nodes for this hypercube? Okay, and imagine that you want to build snapshots in this hypercube of dimension 10. It can involve a very, very important number of snapshots. Okay, if you want to use a uniform discretization of such an hypercube. So here, the idea is to be able to build efficiently in a frugal approach. You want to optimize the number of snapshots in such a multiparametric space in order to reach a given level of accuracy. So you see, it is quite challenging because here, it is clearly the problem of the curse of high dimensionality. If you want to have a small number of snapshots, you have to be efficient in such multiparametric spaces. Okay. So here, I propose to illustrate the strategy that we propose in order to be efficient in terms of complexity and optimization of the number of snapshots with a very simple parametric space of dimension 2. Okay, for instance, a 1D space and 1D time. Okay, here it concerns an hypercube of dimension 2, so it is a square, and you have 4 snapshots here on you can see the different nodes of the square, and we are able to estimate the error with space-time error indicator. I don't give you some detail on this, but imagine that it is available at the middle here of the square, and you can estimate the level of accuracy of such a set of snapshots. Okay, and then if you don't reach the level of accuracy, you refine the mesh. Okay. In this way, for instance, from 1 square to 4 squares, and in the middle of each square, you iterate in the same way, and you proceed to error estimation in space and time, for instance, in order to have an idea of the level of accuracy of this 2D parametric space, and so on. And you can look, the idea here is to proceed to an iterative multiscale process you can make a strong link with multi-grid localized adaptive methods. The idea is to focus only locally in the parameter space where you don't reach the level of accuracy in order to minimize the set of the number of snapshots. Okay, so it seems interesting in order, if you compare to a uniform discretization of the parametric space, and so on, in order at the end to reach the level of accuracy. And in this case, you have a specific number of snapshots. And I recall here that each snapshot is a welding simulation, for instance. Okay, each snapshot is a welding simulation with a finite element software. So it is very important to optimize this number of snapshots. Okay, so here, for instance, it is a very simple one with a level 6-dimensional virtual twin, 3 for time, 3 for space, 1 for time, And here you have the heat capacity and the yield stress as the parameters for such a simulation. Okay, and here we ensure a level of error of 7% with 14 snapshots. Okay, so it is quite simple in this case in order to ensure a good level of accuracy. Another example, here imagine that you want to proceed to real-time control of the welding process. So it can be of interest to introduce in the virtual twin the heat source. During the moving of the heat source, you can increase the intensity of the heat source from Q1 to Q2. So at which time you want to increase the heat source, and also which value for the heat source, okay? You can test it virtually by using in real time the virtual twin, so it is of interest in this case. You can imagine also to use such models by a feedback in order to control the process in real time, okay? So it can be of interest to use such parameters in the virtual twin. Okay, and in the same way, we have to optimize the number of snapshots in order to be frugal, in fact. Okay, what you see here is through video, in the through time, a user is trying to use this virtual twin in order to the quantity of interest in order to test here not the temperature field but the stress field in terms of von Mises. Okay, it corresponds the field here is the von Mises stress. So it can be of interest in order to check the residual stresses involved by the process. Last way to improve the frugality of the virtual twin is to use sparse grid method. It is well known at that time, and it is very, very interesting method in order to build a frugal virtual twin in order to optimize the number of snapshots. So at the end, what we propose in this case is to use a multi-grid adaptive strategy in order to define the position of the snapshots coupled with a sparse grid method. So sparse grid, maybe the best idea is to show you a picture in order to explain how it works. Instead of using immediately a localized multi-grid strategy in the multiparametric space, the idea of sparse grids is at first to focus on the global axis of the multiparametric space, as you can see here. Okay, in order to reach a given level of accuracy on the axis. Okay, and then after that, you check on a specific part if you have also obtained a good level of accuracy. So it is a combination of sparse grids and multi-grid adaptive strategies in the multiparametric space. And it is quite interesting because in this case, we have compared with available analytical solutions of different fields, theoretical fields, as you can see here. And what is interesting in this slide, it is, in fact, in order to build a high order proper generalized decompositions of such fields, it concerns two-dimensional fields with different frequency contents, as you can see here. Okay, you have here, in fact, the sparse grid, multi-grid adaptive strategy in order to be as efficient as possible in the number of snapshots. Okay, and the combination of these approaches, I mean sparse grids and multi-grid adaptive approaches, allows to decrease the dimensionality, the number of snapshots, compared to a uniform discretization of the multiparametric space. So it is of importance in order to optimize the size of the virtual twin, the number of snapshots, because even it is done in the offline stage, it can be quite expensive to calculate all the snapshots in this multiparametric space. So here, I think that it is very, very important to develop multi-grid strategies in order to be efficient in the number of snapshots in the multiparametric space. A last comment here, we can also add the geometrical parameter in the virtual twin. Here it concerns the thickness of a plate. Okay, why not? It is very simple in this case because we can build a linear mapping between the reference configuration and the material one with different parameter thickness, E1 and E2. The idea is to consider a reference configuration between the two models of different thickness. And then in this case, we can also use geometric parameters, even it is quite simple here because it is only a scalar parameter linked to the thickness. However, it can be of interest, even in this case, in this simple case, to improve the welding process. And in the same way, we can iterate here in order to build in a multi-grid strategy an optimization of the number of snapshots. It is a 3D multiparametric space in this case, the heat capacity, the yield stress, and the thickness. So you can see how it works in 3D. And we check for the different fields, temperature strain or plastic strain, if we reach or not a given level of accuracy, here close to 10%. As you can see here, is that two fields are not enough accurate, so we have to refine in the virtual, in the multiparametric space, locally, first of all, following the sparse grid approach, so we refine on the axis, main axis, okay, of the multiparametric space, and then we locally refine on the area of interest in the multiparametric space where we don't reach a good level of accuracy. And in this case, at the end of the process, we can ensure a good level of accuracy of the virtual twin on the different quantities of interest. Okay, and here, a last example of such virtual twins. And the quantity of interest here is the von Mises stress in order to check possible residual stress at the end of the process. And we can here also, as you can see, use the thickness as a parameter. So here you have in real time the transient space-time simulation of the welding process with different thickness. Okay. So in order to conclude with such approaches, for instance, we have tried to develop these approaches until 10 dimension 10 virtual twins, space, time, and 6 control parameters. The only limit, in fact, is the offline stage, because the offline stage can be 1 week or 1 month. Okay, it depends on the number of snapshots. So here it strongly depends on the level of accuracy you want to reach, and also the dimension of the multi-parametric space. And you can use such virtual twins. Here we proceed to PCA projection in order to plot the snapshots. So it is in fact a way to see in a subspace of dimension 3 what happens in a multiparametric space of dimension 10. So we, in fact, we project a multiparametric space of dimension 10 on a space of dimension 3. This is what we call the PCA projection in order to see where globally are the snapshots according to 3 interesting parameters. Okay. And okay, is a summary of the global strategy, the offline stage and the online one, and many possible applications which are of interest for Framatome or Électricité de France, for instance. There are many possibilities now if you have dedicated virtual twins in order to study in detail what happens in a welding process. Here are specific models, well known. In this case, sorry if I come back to the previous slide, TG4 is an attempt to develop, in fact, a numerical standards for welding. Okay, and also according to specific experiments, in order to understand in the bulk, in detail, the residual stress from experiments, and also to be able to develop a reference numerical model in such a case in order to have a good modeling of what happens in such an experiment for all the fields. I mean, temperature fields, mechanical fields, and so on. And the interest of such an experiment, numerical standard and experimental and numerical standards, is that we can compare experiments. We have data experiments in the bulk. Here, if we compare the transverse stress or longitudinal stress here in this experiment, in a specific area of interest in the bulk, in black, you have the experimental data, okay? And here we have built a very simple virtual twin with only one parameter. I mean, if you consider space and time plus only one parameter, which is k, it's a factor multiplies the yield stress. Okay, if k equals 1, then here you have the yield stress that you know in this case. Okay, but here it can be of interest to modify the value of the yield stress in order to be in good agreement with the experimental data. And even with a 1D very simple virtual twin, we can see that we can adapt the value of k according to what we call the yield stress. Okay, so it is a very simple example, but even in this case, we can see that the virtual twin is not so bad compared to the data, and then we can identify the value of k according to the data. Okay, we can also proceed to process optimization on it, on the temperature field. Okay, and we can conclude this first part on, for instance, virtual twin dedicated to the process optimization for a given distortion. Imagine that in a given, for instance, in this case, when you have a T-joint welding, okay, you can be interested in the distortion effect in such a welding simulation. Okay, so if you develop, for instance, a virtual twin with space-time and 3 other parameters such as thermal capacity, modulus, and total heat flux, you can check the value of the distortion, maximum distortion, in the multiparametric space. So imagine, in order to plot this, it can involves a lot of finite element simulation if you want to proceed step by step according to the value of the parameter. But if you have built offline such a virtual twin, you can obtain in 1 or 2 minutes the optimization according to the 3 parameters of the subspace of the multiparametric space where you reach the condition that the distortion is smallest than a given value. Okay, so it can be of interest also to optimize a specific quantity of interest very quickly. It is not exactly real time, but here it can be very fast, and it is an interesting using also of virtual twins in such a case. Okay, so in order to summarize the general strategy that we have developed this morning, first of all, it consists in an efficient and frugal database generation. I mean a snapshot, a set of snapshots, and each snapshot is a space-time transient nonlinear simulation, which can be, in terms of finite element simulation, very expensive in terms of CPU time and so on. So instead of doing this, each time you modify a set of parameters, we propose an offline stage, a learning stage, okay, based on separated variable representation, sparse grid, multi-grid, adaptive strategy in order to optimize the number of snapshots for reaching a given level of accuracy, and also in terms of storage. And then from this strategy, what we want at the end is a numerical twin, digital twin. Okay, I don't make the difference at this level of the discussion. Physically based. Okay, physically based. And also which allows to use the virtual twin in real time. Okay, and the key point here in this case is to be able to build virtual twin based on a separated variable representation of the different quantities of interest, the different fields involved in such simulations. Okay. And we can add also the fact that in the learning stage, when you have finished the learning stage, you can use a virtual twin that in the same way as we have explained before, but also you can come back to the learning stage and you can also increase and improve, if you want, the virtual twin with more quantities of interest. You can add parameters. You can add parameters, new parameters, okay? You improve the level of accuracy, okay? You can keep previous virtual twins in order to improve their ability to be better in the using in real time of such a virtual twin, okay? You can add new parameters, increase the level of accuracy, and so on. So globally speaking, what I propose here is based on learning, a global learning strategy, a posteriori non-intrusive strategy for the construction of virtual charts or virtual twins. It is mainly based on the high order proper generalized decomposition. What we want is the answer of the virtual twin in real time. We don't want to proceed to physical simulations during the online stage. Okay. Furthermore, we have to optimize the virtual twin in many ways. First of all, we have to optimize the size of the virtual twin in terms of number of modes. Here, it was interesting to notice the effect of the moving frame of on the thermal field, temperature field, sorry, and also a very efficient and multiscale adaptive selection of the snapshots, a combination of local multigrids and sparse grid, and also acceleration techniques for the high order proper generalized decomposition, and then optimization of the memory storage and frugality are of great importance in the definition of such virtual twins. And at the end, as I have explained before, the control of the accuracy. And last but not least, non-intrusive data generation based on, for instance, finite element software.